Okay, so here we will put flip-flops together. We did, that started with the tubes and then gates, flip-flops. Now, how do you put flip-flops together to make to make registers and things and everything else that goes in this computer? So, um, this is called a synchronous design, and what that means is the way I picture it is all the flip-flops in the whole thing. I picture as being in like a big vertical column like this here. So I'm going to draw, a couple flip-flops here. But all the flip-flops, and there are 50 flip-flops in this computer, so all the flip-flops means 50, right? So we take all the flip-flops here, they're all D flip-flops. Again, try to keep it simple as can be. So I take a bunch of D flip-flops. Now the thing that makes it synchronous is all the clocks are connected together. They all clock at the same time, okay? So you have a clock signal that goes into all of these. Okay, so a common clock. So we connect all these clocks together. And so I think of this big crank here, right? The clock goes ker-chunk, 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 right? Every cycle. Now, on the output of these flip-flops, of course, you have the Qs. Well, you have the Q bars too, but Qs, you can put Q bars on here too as well. And what happens here is there's a bunch of combinational logic here, right? Some gates, OR gates and AND gates and NANDs and NORs and all kinds of stuff on here, right? Connected to all these flip-flops, blah, 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 blah. And then these loop around and go to the various D inputs, right? So there's a bunch of the idea is you have flip-flops here and ker-chunk, right? The clock clocks some state in every clock pulse. And then it soaks through all this combinational logic, comes back around, and has to be ready in time to for the clock on the next ker-chunk, right? Next ker-chunk. So might have some NANDs and NORs and whatever you got here, OR gates and whatever you got connected to various inputs. So ker-chunk on the clock, and that starts sending signals out here, and they soak through the ands and ors and all of that stuff, and they all have to be ready around here, and then the next clock cycle ker-chunks them in, and then they soak through the new values. Some of the flip-flops change, some of them don't. The new things go through there, go back around, and it's ready for the next cycle. So that's a synchronous design. All the flip-flops ker-chunk at the same time. Okay. Now, specific to this design here is even the Raspberry Pi can be thought of as a big flip-flop. So here's like the Raspberry Pi. I'll put RASPI on that. I don't know how well you can see that in the video. But, and it has a bunch of D inputs. I can't remember, over a dozen inputs and a bunch of outputs. And again, they go to these gates, a bunch of these gates too, and they get a bunch of outputs from some other gates, right? But it's just a big flip-flop. And it can be thought of as having a T input as well. But the Raspberry Pi generates the clock. But, logically it's the same. Still there's a clock edge ker-chunk, right? And ker-chunk, ker-chunk, ker-chunk. The Raspberry Pi actually generates the clock. But, as far as this is concerned, it can be thought of as, it's receiving a clock. Okay. And the reason why I have the Raspberry Pi generate the clock instead of it, inputting a clock to the Raspberry Pi to have it do something is in case Linux decides it wants to, wear level some flash memory or something like that. All it'll do is stretch out the clock cycle. It won't miss anything, and it won't try to rush anything. So that's why I have the Raspberry Pi generate the clock. Anyway, but again, it can be thought of logically as, Kerchunk it outputs its stuff like, oh, it read some values from memory, or it's, generating an interrupt request or something like that. It soaks through this logic here. It comes back around here. Um, and this logic here might be telling it, oh, I need the Raspberry Pi to read a memory location or write a memory location. So that would be part of the control logic, signals going in here and data signals going in here. This might be an accumulator flip-flop, and this one down here might be, oh, the fetch 2 flip-flop or something like that. And all comes around Kerchunk, and then that soaks through these gates here, all comes around Kerchunk, right? So one thing with this design is that some of these paths might be more logic gates than others, and it takes longer for the signals to get around. And you just have to say, well, okay, I'm just going to do this worst case timing. Um, and that's, sort of a downside of this design is that you sort of use worst case timing, because maybe you could speed things up if you know, oh, this cycle is only going to go through a short circuit, not a shorted circuit, but just, a few number of gates to get around, and you could make that cycle a little quicker. And I actually have two categories of clocks in this um, processor design. So this clock will actually run at two different speeds depending on what it's doing. It'll run a slower clock cycle if I'm having the ALU do an add, because that's a 12-bit add, and even with the carry look aheads and all of that stuff, it's still advantageous to do a slightly slower clock for anything that's doing an ALU add cycle. Any of the states that it's an ALU add will run a little slower than all the others. But other than that, still it's a Kerchunk. Here's the beginning of the cycle, and the stuff soaks through the gates, comes back around, and is ready for the next Kerchunk, right, on the clock. So that's basically a synchronous design. Okay. Now, you might say, okay, well, here are all these clocks, all these flip-flops clock on the same clock the whole time, each and every time, okay? But what if you don't want, you just, like, this is an accumulator, let's say this is an accumulator, for example, a bit of the accumulator, and we're not loading the accumulator this cycle, okay? So what do? We have two choices. We can either have this logic here determine that, oh, we're not loading the accumulator, so that's the same as putting the same value back in the accumulator each time, and it can be done that way. Okay. Um, in my design, the program counter works that way, and all the state flip-flops like fetch 1, fetch 2, the 3 defers, the 3 exec flip-flops, they work that way. They all get clocked every cycle. But to save some gates and save some tubes, I actually gate the clock on the accumulator. So the clock really doesn't go every cycle on the accumulator. Okay, it only clocks on the cycle that I want it. So it's not, a fully synchronous design in that sense. But when it does clock, it's clocking at exactly the same time as all the other stuff. Okay. And it's very important. You don't want to have this one clocking a couple microseconds after this one, or after this one, because then some of the state will leak through. You want it to go, okay, it's either fully in the state before or fully in the next state. Okay, you don't want to have some of these things going clock, 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 all in at different times. You want them all to Kerchunk at the exact same time. Now, like I said, there's 50 flip-flops here. So you actually need some clock drivers here. So you have these run through a bunch of couple of inverters, right, to bolster the clock. And I'll get to the gated clock here in a second. And the way this works, so there's like an inverter here. So two inverters means, okay, it's just amplifying the signal and making it greater. And there's not just one inverter here, there'll be like a bunch of these. Okay, so you might have a couple of inverters for the program counter, a couple of inverters for the accumulator, and a couple of inverters for, the other registers that need to get clocked. So this is really driven by a bunch of inverters. Okay. But it's all driven by exactly the same number of inverters, okay? So from this signal, the clock signal coming in, okay, it always goes through exactly two inverters before it goes to the D flip-flop, so that the timing is the same, right? And that way all these end up being clocked at the same time. And in the source files and stuff, I call this clock 2, because there's two levels to go before you get to the flip-flop. And I call this one here underbar clock 1. There's one level left before I get to the flip-flops, and then I have clock 0, CLOK 0. Okay, and the clock 0 is the only one that can actually go into a flip-flop. Clock 1 is inverted, and so it has one more inverter to go, and that comes from a clock 2 signal, and clock 2 is what comes out of the Raspberry Pi, actually. Okay, so now if I want to gate the clock going to the accumulator, all I have to do is make a little NOR gate here, I think it is. So make one of these inverters into a NOR gate, and then I can turn the signal on and off to gate into the accumulator. If I don't want the accumulator to run, all I have to do is drive this high. If you put a 1 in there or drive it high, then it will just block the signal from this clock signal from getting through, and force the accumulator not to load that cycle. But when this signal is low, to enable the accumulator to load, notice it's still exactly two inverters worth to get to that clock signal there. I couldn't, for example, put an AND gate right here, because that would be another level of gate, and it would throw the timing of the accumulator off. So you wouldn't want to do that. You want to gate it back here in these drivers. Okay. So anyway, that's the idea behind the synchronous design of it. You get everything kerchunk, and then it soaks through all these gates here, comes back around, and is already here, gets here in time, just in time for the clock. In the worst case, kerchunk, goes out here, comes back around, So you get, like, when you start, like, it's fetch 1, okay? So all these things are, it's sending the program counter to the Raspberry Pi and telling it, oh, I want you to read memory, and then the clock cycle comes, and the Raspberry Pi knows, oh, that's a read memory thing, so it's sending the opcode out here, kerchunk, right? And then it goes into the next fetch cycle, and it gated that around to the instruction register as some flip-flop in here, and it kerchunked it around and kerchunks it into the instruction register, right? And then that soaks through all these gates, decoding the instruction, for example, and comes back around here and has everything ready for what the registers need to be the next cycle. Kerchunk, okay, maybe it goes into defer 1, because it was an indirect memory instruction that got loaded into the instruction register. And now the defer 1 flip-flop, wherever it is amongst all these flip-flops, will be set, and then it will output its stuff there telling the Raspberry Pi, oh, you need to read the memory pointer and things like that. And it just keeps going kerchunk, kerchunk, kerchunk. All these flip-flops go at the same time. So that's the basics of the synchronous design of the thing. Okay. If there was, like, you had an external interrupt request line, okay, that would go into one of these flip-flops here, and it would get synchronized with this clock, right? So that it would not be asynchronous. Okay, it would need to be synchronized with a flip-flop, and then it could follow this simple logic pattern of flip-flop here, and then all these gates, combinational logic only, come back around and get ready to get clocked in for the next state. Anyway, that's it for the synchronous design. So that's putting the flip-flops together to make the processor, and that's how you stack them together, and it just makes for a very simple design. I don't have 3, 4, 5 phase clock craziness going on. All right, so it's just, again, just a way to make a simple design, simple, reliable design. All right, so that's it. Next will be how to, or how in this processor, what registers I use and all of that stuff. So that's it for this one. Hope that was entertaining for you.